everyone. Our next topic for module 1 is the kinetic model of gases. So after studying this module, you should be able to accomplish the following outcomes. First is to describe the kinetic molecular theory model of an ideal gas. Second is to apply the kinetic molecular theory equation for the calculation of the pressure of the gas. And lastly is to calculate the kinetic energy of gas molecules. Now, in terms of properties of gases, if we will be comparing gases with liquid and solid, so we know that gases have lower densities compared with liquids and solids. And in terms of compressibility, the compressibility of the gas is much higher compared with liquid and solid. Now, in terms of compressibility, an external pressure also must be applied to contain a gas. And you know that different gases diffuse into one another. So different gases completely mix in a homogeneous fashion. So the diffusibility of gases can be attributed to the motion of molecules and to the lack of intermolecular attractions. So the gas molecules have a great tendency to escape if a barrier confining it is removed, since it's not held back by any attraction of other molecules. Now, recall in our ideal gas law equations, all of these are derived empirically. Example, the experiments of Boyle, Charles, Avogadros, and even Daltons. So they did experiments, they made measurements, observed trends, and made generalizations. So keep in mind that they are empirical and don't tell the molecular nature of gases. Now, in this topic, so we will be considering the kinetic molecular theory. So the kinetic molecular theory is a model used to discuss the molecular basis of an ideal gas behavior. So we know that gases are a collection of point particles. So they are moving very fast and in ceaseless random motion, colliding sides of their container. So what are the basic postulates of the kinetic molecular theory? So number one is gases are composed of discrete particles like molecules or atoms. So this is a known information already. So number two, gas molecules are in random, ceaseless, linear motion. So they collide elastically with one another and against the wall of the container. So when we say collide elastically, so this means that no kinetic energy is lost. So they could not transfer momentum here. Now, third postulate is the molecular size is negligible. So the distances over which molecules travel are much greater than molecular size. So volume occupied by gas molecules is neglected. So this means that actual volume is so large compared with gas molecules. So it's appropriate to be considered them negligible. So thus gas can be coined or termed as point particles. And lastly, molecules are treated as hard spheres. So they make perfectly elastic collisions with one another and the sides of the container. So this means that they exert pressure, but they don't lose the energy during collisions. So all energy is conserved. So if we will be considering kinetic model assumptions 3 and 4, we will realize that this neglect volume of gases in terms of molecular particles. So these are the limitations. So there's no intermolecular forces of attraction between molecules. And if we will be considering the total energy, which is the sum of the kinetic and potential energy here is zero. So the total energy refers to the kinetic energy. So that's why it's called kinetic molecular theory. So it involves translational motion of gas particles. So when we say translational, the motion that involves sliding of one object into one or more dimensions X, Y, and Z. Now, for us to understand more the derivation of kinetic molecular theory equation, so we will be considering a certain gas enclosed in a cubic box at constant temperature. So the length here is termed as L. So the total number of gas molecules is N, mass of one molecule is M, and the velocity of a molecule is V. So if we have axes X, Y, and Z, the velocity for each molecule is equal to V squared is equal to Vx squared plus Vz squared plus Vy squared. So as mentioned earlier, the pressure of the gas is caused by collisions of the molecules with the wall of the container. So gas here can be pictured as being made up of a great number of molecules. So thus example, in 1 cubic centimeter of a gas at 25 degrees Celsius and 101.3 kPa, there will be around 2 times 10 raised to 19 molecules. Now, remember that no need to memorize these equations. Our goal here is for you to understand this more. So for us to derive the postulates of kinetic molecular theory, so we're done with expressing this in terms of postulates. Now we will express this in terms of mathematical symbols. And then we will understand more the microscopic properties. So what are those microscopic properties? Speed of molecules, molecular mass, number of molecules, and we will relate this to macroscopic properties like pressure, volume, temperature, and even number of moles. So example, if you squeeze a balloon, so you'll feel in your hand the force of gas molecules pushing towards you. So pressure here is a macroscopic property. So, but if we will relate this into molecular basis, so we will understand, we will try to understand more the collisions. So the steps here is we will be considering the number of collisions on a wall due to a single molecule. Next is we will determine the force due to collision on a wall due to one molecule. So in this slide, so example, if we will be before we discuss the change in momentum, so our step here is to understand more the number of collisions due to a single molecule. And then the force relating due to a collision of single molecule. Now the force due to all molecules colliding in all walls, and we will relate this to pressure. So in here, so if we will be considering the change in momentum of a single gas molecule, so example, if we have walls here A and B, so before collision, the momentum here, the change in momentum is equal to mvx. So, but after collision, since we are referring to same axis, so after collision, momentum is negative mvx. So as the molecule moves to the right, it will eventually collide with the wall and then move to the left. So before collision, the momentum here is mvx, and since the collision is elastic, the momentum of the molecule after collision will be equivalent to negative mvx. So recognize here that momentum is a vector quantity, so that it changes its sign as the direction of the motion changes. So therefore, if we will be considering the change of momentum per collision, mvx, negative mvx, so it's this referring to change. So negative times negative, so the change of momentum, that's our first step, per collision is equal to 2 mvx. L here is referring to distance A and B. Now, if we will be considering the time time is equivalent to distance over speed. So example, from A to B, time is equal to distance L all over Vx. So from B to A, so this is A, time is also L over Vx. So time as a molecule travels from point A back to point A. So A to B, then B to A, L over Vx plus L over Vx. So this is equal to 2L Vx. So if we will take the reciprocal, because to get the number of collisions on A per second. So we will take the reciprocal. So therefore, our second equation is collision on phase A per second is equal to Vx over 2L. Now, if we will get the total change of momentum on phase A from 1 molecule per second, so we will get the first equation that we got earlier, the molecule per collision, 2 mvx. Then the second equation, collision per second, Vx over 2L. So we will get mvx squared over L. So what does this mean? What does it mean? So this is the total force on the wall due to collision of a single molecule on x-axis alone. Now, so that's x-axis. Now, if we have to get the total force on the wall due to the collisions of one molecule on x-axis, two collisions on wall A and on wall B. So the total force on the wall due to collision, so this refers to mvx squared over L on wall A. And then on wall B, we have mvx squared over L. So this is equivalent to 2 mvx squared over L. Now, expanding this to all sides of the box to have one molecule. And we will be considering here the three axes x, y, and z. So 2 mvx squared over L plus 2 mvy squared over L plus 2 mvz squared over L. So we will combine the common factor 2m over L, and this is equal to v squared. So for a single gas molecule, 2 mv squared over L is equal to force. So in this case, we are considering all sides x, y, and z. But if we will expand this to all molecules, so remember we're done with considering a single molecule. Now, to understand this, we will assign n as we will denote n as referring to all molecules. So not all molecules will travel with the same velocity like v1, v2, and v3. So keep in mind here that we are dealing with same molecules. So F total is 2mv1 squared over L plus 2mv2 squared over L. So 2mv3 squared over L. So common factor 2m over L. And v1 squared plus v2 squared plus v3 squared. So let's assign n. So if we have to multiply this by the number of molecules, so all over 1, so this is over n. So rearranging the equation, 2mn over L multiplied by this term. So remember, this is equal to the root mean square speed, or in other books, this is called RMS. So this refers to the sum of all velocities per total number of molecules. And take note that this is different from average speed that will be mentioned later. So remember, U here, U squared, refers to the root mean square speed, or RMS. Now, if we will relate the force of collision on walls to pressure, so what is the formula? Pressure is equal to force per unit area. Area here, so we are considering cube, 6L squared. So substituting 2m and u squared over L all over 6L squared. So we will have the equation 1/3 m and u squared all over this L cube becomes volume. So after considering the steps, So we derive now the kinetic gas equation equal to PV equal to 1/3 mNu squared. So if we will compare this with root mean squared, so which is a microscopic property. So we could say that pressure is directly proportional with root mean square speed. So this is the kinetic gas equation now. PV is equal to 1/3 mNu squared. But the question now is, can we apply this kinetic gas equation to a spherical container? So if we will relate this to kinetic energy, so the equation, our equation earlier is 1/3 mNu squared. So if we will add 2/2, and then we interchange the numerical values 1/2, and then we have the constant 2/3. So take note that this is referring to the kinetic energy. So kinetic energy is 1/2 mNu squared. So if we will get the product PV in terms of kinetic energy, PV is equal to 2/3 of the kinetic energy. So from the ideal gas equation, PV is equal to nRT. So therefore, the kinetic energy, this is equal to 3/2 PV. Or in terms of nRT, kinetic energy is equal to 3/2 N multiplied by R multiplied by T. So as a moving gas molecule possesses kinetic energy, which is dependent on the mass of the molecule and the velocity, so this is expressed by the following equation. As I mentioned earlier, 1/2 mU squared. So we derived this earlier. Kinetic energy is equivalent to 3 PV halves for a single molecule, and ideal gas is PV is equal to nRT. So for a 1 mole of a gas, kinetic energy is 3 RT/2. So from the derivation in terms of force, pressure, then relating to kinetic energy, so kinetic energy is just simply saying 3 nRT/2. And if we have 1 mole of a gas, so this is 3/2 RT. Now, if we will be considering one molecule, so 1N is equal to 1/NA from the number of gas molecules. So the equation becomes 3/2 RT/NA. If we will relate this with the Boltzmann constant, kinetic energy, another form of kinetic energy is 3/2 kT. So K here is the Boltzmann constant, which is equivalent to R/NA. And if we will relate the kinetic energy, which is a microscopic property, to a temperature, which is a macroscopic property, so we could say kinetic energy is directly proportional with temperature. Now, this is a simple problem on calculation of average kinetic energy. Calculate the average kinetic energy of 1 molecule of oxygen molecules at 27 degrees. So our equation is 3/2 nRT. So we have 1 mole. So the value of R that we will be using is 8.314 joule per mole Kelvin multiplied by temperature in Kelvin. So we have 3,743 joules or 3.74 kilojoules. Now, if we will, another form or derivation of the kinetic molecular theory, so our equation earlier is PV is equal to 1/3 mNu squared. So again, M here is the mass per molecule. And capital N refers to the number of molecules. So if we will be considering here, so this refers to the mass of the gas. So capital N is the number of molecules. So this quantity can be calculated from number of moles. So N is equal to the number of molecules is equal to the number of moles multiplied by Avogadro's number. So mass of each molecule can be calculated from the molar mass, capital M, multiplied by Avogadro's number. So mass is equal to M over Na. So if we will be substituting 1/3, M here is M, capital M over Na. And capital N is equal to N multiplied by Avogadro's number, Na. So this will be cancelled out, Na. So another form of the kinetic molecular theory, Pb is equal to 1/3 N. What is N here? Number of moles. Capital M is molar mass. And root mean squared. So this form of KMT involves a number of moles, molar mass, and the product Nm here gives the total mass of the gas molecules. So from the KMT equation, PV is equal to 1/3 N capital M U squared. And ideal gas equation, PV is equal to nRT. So substituting or equating both sides in terms of PV, nRT, 1/3 NMU squared. So N would be cancelled out. So RT is equal to 1/3 capital MU squared. So the root mean square velocity is just equivalent to 3RT all over molar mass raised to 1/2 or square root. So this is what we call the root mean square speed or velocity. So a simple problem on molecular velocity is calculate the root mean square velocity for of oxygen molecules at 25 degrees Celsius. So we will apply the equation that we've derived earlier. U is equal to square root of 3RT all over molar mass. So what's the value of R that we will be using? 8.314 joule per mole Kelvin. So joule is equal to Newton meter. And Newton is equal to kilogram all over, kilogram meter per second squared multiplied by meter kilogram m squared over s squared. So 3, so we will be substituting 8.314 kilogram m squared all over second squared all over mole Kelvin. So convert the temperature to Kelvin. And this is oxygen molecules, O2, diatomic, 32. So take note, this is the common error. You need to convert this to kilogram. 32 times 10 to the negative 3 kilogram per mole. So in order for us to get the root mean square velocity for a certain molecule at a certain temperature, so we will be applying square root of 3RT all over molar mass. So we will be getting 482 meter per second.